Hi everyone. So I want to talk in this video about how to find the inverse of a matrix. And so last class we talked about if a matrix A is n by n, then we had this theorem called the invertible matrix theorem. Matrix theorem. So if A is n by n, then the invertible matrix theorem tells us when A is invertible. And there were 12 equivalent things listed, one of which being that A is invertible. And a few people used different things on this list to argue that one of the matrices was invertible on the handout from last class and one of the other matrices wasn't. And a couple of things that people used were this item C, that A has n pivot positions. And another group used item D, that the equation AX equals the zero vector has only the trivial solution. But what we can notice about both of these things is that they lead to this option B, that A is row equivalent to the identity matrix IN. And so both of these involved taking my matrix A and then putting it in reduced row echelon form, or at least starting the process of putting it in reduced row echelon form, and then determining that it had these n pivot positions, which then meant that we could continue reducing it to the identity matrix. And okay, so that tells us how to find the inverse of a matrix, but what if we know that a matrix A is invertible? Then how do I actually go about finding that inverse? And there's the following theorem in the book, which says that any sequence of row operations that reduces an n by n matrix A to the identity matrix IN also transforms IN into A inverse. Okay, so what does that actually mean? So in other words, or translation, if we form the augmented matrix with A on the left and the identity matrix on the right, and row reduce this matrix so that I'll say the A part looks like the identity. So if possible, can't always do this, then the identity part will be A inverse. So in other words, I have this matrix, this augmented matrix that I formed, and if I can row reduce then it will look like the identity matrix here and A inverse over here. So with my matrix A, I have a bunch of row operations that I'm performing on A. And when I'm doing that, say I want to multiply this first row by 1/2, I'll multiply the entire first row by 1/2, including what's over here. So as I'm changing A, I'm also changing my identity matrix, and the result will be this. And so I want to look at an example. So let's say our matrix A is the following. So 0, 1, 2, 1, 0, 3, 4, -3, 8. And I want to know the following. So question 1, is A invertible? And question 2, if so, what is A inverse? And I'm going to say that we can actually sort of hit two birds with one stone. And so what I can do is, so solve both Q's at once, is I can form my augmented matrix. So let me form this: 0, 1, 2, 1, 0, 3, 4, -3, 8, 1, 0, 0, 0, 1, 0, 0, 0, 1. And then I can perform row operations on it to try and get my matrix A to look like the identity matrix. And so one thing I might do is, if I want A to look like my identity, then I need to have a pivot in this first position. So I'm going to replace row 2 with row 1. So I'll do an interchange with these. And so when I do that, I get 1, 0, 3. But notice I need to interchange this entire row with this entire row. So now over here I have 0, 1, 0. And then I have 0, 1, 2. And 1, 0, 0. And then this third row stays the same. So 4, -3, 8. And then 0, 0, 1. And I'll do one more, and then I'll talk about how we can kind of shortcut this process. And so let me take 4 times row 1, and I'm going to subtract that from row 3. So that'll get me a 0 in this position. And so off to the side, 4 times row 1 would be 4, 0, 12. 0, 4, 0, and I want to subtract that from row 3. So 4 -3, 8, 0, 0, 1. And then I'll replace row 3 with this. So when I do that, this one stays the same. 0, 1, 0. This one, second row, also stays the same. But this row now becomes 0, -3, -4, 0, -4, and 1. Yeah, so I have my row 3, and then I'm subtracting row 4. Okay, but again, the important part to notice, or to emphasize, is that anything I do to this part on the left to try and make it look like my identity, I am also doing to this part on the right. So even though I'm drawing this line to divide the two, this is one giant matrix, so I can't just act on the left without acting on the right. Okay, so let's say I continue this process, and if I were to do all of this and keep row reducing, what I end up getting is the following. So end result. And I end up with an identity on my left side. and that's because A is invertible. So A row reduces to this, which means it has a pivot position in every row. If I wanted to solve the matrix equation AX equals 0, the only solution would be the trivial solution. All of these things from the theorem are true. I know that just because I can row reduce A to my identity matrix. And what's on the left is negative 9 halves, 7, negative 3 halves, negative 2, 4, negative 1, 3 halves, negative 2, 1 half. And so again, so this is the identity, and the theorem tells us that this is A inverse. So this implies that this matrix, negative 9 halves, 7, negative 3 halves, negative 2, 4, negative 1, 3 halves, negative 2, 1 half, is the inverse of A. And if I wanted to verify this, well, I would take my matrix A and I would multiply it by this inverse, and then I would show that that's equal to the identity. I also could have done this multiplication, either one. Okay? And so that would be the verification. And now the question is, how could I shortcut something like this? So we very quickly stopped doing all of the row operations. And so what I'm going to say is that actually I can enter this matrix, this augmented matrix, in our reduced row echelon form calculator. And if it row reduces with the identity on the left, then what follows on the right will be A inverse. And the reason for that is the operations, when putting something in reduced row echelon form, the operations that we're doing are still the same. So I'm doing interchanges, I'm multiplying by scalars, I'm adding and subtracting rows, but what I'm not going to have a pivot position in, the first column, second column, and fourth column if I can have it in the first, second, and third. So if I put this in my reduced row echelon form calculator, in this augmented form, the proper end result will still occur. So if it's possible to put your matrix A to row reduce it to the identity matrix, then the calculator will still do that, and this A inverse will follow on the right. So if you can't do that, and we know from last class the second example was not invertible, so I encourage you, if you put that one in the reduced row echelon form calculator with the identity on the right, you'll see that when you row reduce it, you do not get the identity over here, and so that tells you that A inverse does not exist. And so in practice, is that enough? You would need to say specifically, is that enough to argue that the matrix is not invertible? And when doing that argument, you would need to focus here and say, no, A does not row reduce to the identity matrix, so therefore it's not invertible. Okay,